It's a pleasure to still be here after 12 days. Today I'll speak about some work I've been doing with many people in the past years, trying to understand basically how conformal field theory arises in the study of statistical mechanics models, something that has been understood from the physical perspective about 25 years ago, but that mathematicians would, and especially probabilists, would really like to understand well, because it's a beautiful collection of ideas, and that should give a collection of beautiful mathematical statements. So I'll speak mostly about the Ising model, as just a little bit about the Gaussian free field. And for those who have seen this talk, I decided to change a bit the end to re-explain some ideas in a way that I think is more understandable. So you don't need to sleep for the whole talk, only the first half of it. Okay, so what is the Ising model? So the Ising model is a model that lives on a graph. You have a graph, and on this graph you have plus ones or minus ones. On the vertices of this graph you have plus ones and minus ones, as Wendelin discussed this morning. In this talk, we'll consider the Ising model on the square grid, the two-dimensional Ising model. And in order to make the connection with geometrical ideas, we'll actually look at the Ising model on various domains of the plane. So what is the Ising model on a domain of the plane? You take your favorite domain of the plane and you discretize it by a fine square grid of mesh size delta. So you get a finite graph if you had a finite domain. And the Ising model, as I said, is an assignment of plus minus 1 spins to the vertices of the graph. And the probability of a spin configuration is given by its Boltzmann weight, exponential of minus beta times the energy. Beta is a positive parameter, the inverse temperature, and H, the energy, is the sum over all pairs of adjacent vertices of the graph of minus the product of these plus minus ones at the endpoint. So what you're doing is you're favoring lower energy configurations. You're penalizing a configuration by exponential of minus times beta times the energy. And what the energy measures is the local disorder in the system for if two adjacent spins are opposite, they add 1 to the energy, while if they are aligned, they subtract 1 from the energy. So you favor local alignment, because you penalize local disorder, and how much you favor local alignment depends on the magnitude of beta. So the goal is to understand what the Ising model looks like at a large scale. We can think of this domain as a window on a possibly larger domain or the whole plane. And we'll often need to speak about boundary conditions. So boundary conditions are just a prescription of the behavior of the spins on the boundary. In order to encode whatever occurs outside, you just need to explain what occurs on the boundary, because the energy, the local, is made of local terms. So you have this so-called domain Markov property that also was discussed quite a lot in the past weeks. Okay, so that's the model, and the question is, what does it look like when the square grid is fine? So the answer is that it depends a lot on beta. So small values of beta, you will see basically a disordered picture here. You have plus boundary conditions, so the plus 1 spins are drawn in blue, and you have the minus 1 spins drawn in green, and you see a completely disordered picture for a fairly small value of beta. While for a larger value of beta, this plus boundary causes the system to actually mostly align in the plus 1 direction. You see almost only blue, meaning plus 1 spins. And so it means that really these boundary spins have influenced their neighbors, and so on and so forth. That's actually how the simulation went. And in the end, everyone is almost aligned. So this is supposed to model magnetism, for instance, or any order-disorder phase transition, where you go from a disordered state to an ordered state in a fairly abrupt manner, depending on how a parameter varies. That's like the critical value for the FK model that Wendelin spoke about. So, okay, we are interested in large scale, and as I said, you have a phase transition. This can be written precisely. You have a phase transition at a precise value of beta for the square lattice, below which you disordered above which you ordered. This can be made extremely quantitative. For instance, you can compute exactly a large distance correlation of spins. So how much a spin here in terms of a spin there? Well, the answer is that if beta is smaller than beta critical, in the long range you just zero. There's no influence. While if you're greater than beta critical, you have a positive correlation at all distances. Okay, so that's a classical model. This was understood almost 60 years ago, 70 years ago, and this is what people still work with, and to understand many features, of the world, how many natural macroscopic structures arise from microscopic ones. Okay, so what we're interested in this workshop is conformal invariance and critical systems. So that's how the Ising model looks like at a critical temperature. The claim of this talk is that you can see many things somehow in this picture that are beautiful and connected with conformal invariance and algebraic structures and SLE and Brownian motion and random fractals, etc. So what do we see at this critical value of beta as the mesh size goes to 0? So we see a scaling limit. So the idea is that you see fluctuations at all scales. So if you zoom out in the right manner, what you will see is macroscopic randomness. So you can hope to see macroscopic or continuous random objects like SLE. And conformal invariant, well, that's of course the assumption, the expectation one has when dealing with such situations. And universality is, well, Wendelin spoke a lot about it. Just a simple example: if you took the Ising model on the triangular lattice, what you would see is a different value of beta critical, but what you would see at that critical value of beta would largely be the same as what you see here. Okay, so what do we mean by conformal invariance? What does it mean that we get conformal invariance for the scaling limit? It means the following. It means that if you take any domain of the plane and any conformal image of that domain of the plane, and you compare the scaling limit of the Ising model on this domain and the scaling limit of the Ising model on that domain, what you have is that if you take the scaling limit of the model, whatever it is, be it a collection of curves, of random fields, etc., if you map it by the conformal map, you obtain exactly the scaling limit that you obtain separately in this domain. Okay. So again, this is fairly loose. What is the scaling limit of a model? So there are mainly two types of objects that we would look at: the probability, the random fields of the model, and the random curves of the model. The former ones being conjecturally described by conformal field theory, the latter one being conjecturally and now, in many cases, provably described by Schramm-Loebner evolution. So that's a general idea that should happen for most of the nice models. What makes the Ising model special? Why is it I speak about the Ising model and not another model? It's because the Ising model has some extra features that allow us to understand this precisely, at least much more precisely than most other models. The idea is that the model possesses some exact solvability on the lattice level, some relations. We spoke a bit about them last week. These were first revealed by Onsager and then rephrased by Kaufman and then rephrased by a sequence of people. And eventually, when found the right rephrasing to address such questions. So we have something perhaps miraculous on lattice level that allows us to actually understand what this means. And that's the reason why I speak about the Ising model. Okay. So let me start by first giving a quick overview of recent results in that direction. So let's start with the random curves part. Okay. So informally the statement is that the Ising model interfaces converge to SLE. Well, what kind of interfaces? What kind of SLEs? Well, you can make many statements. here a few statements. Ising interfaces, the most natural interfaces, if you look at this random collection of plus minus 1, you know, the most natural collection of curves by which you would describe this picture is just a collection of curves that would separate two phases, the plus 1 spins, the blue spins, from the minus 1 spins, the red spins, say. Okay? What happens if you try to describe these random curves that arise in the scaling limit? Well, I mean, you know, to first fix a curve, the most natural setup is the operation boundary condition setup. You take a domain and you split the boundary into two arcs. One arc, you put plus boundary conditions, you put plus spins on that arc, and on the other arc you put minus spins. So this generates spontaneously an interface that will separate the minus spins from the plus spins, so get a random curve, and the statement is that this random curve converges to SLE 3. That's the result of Smirnov, Chelkak, Duminil-Copin, Kemppainen, and myself. If you consider other boundary conditions, there are actually three types of boundary conditions that are conjecturally giving rise to conformal invariant curves. So if you relax these boundary conditions, you allow a third arc to be free, meaning you don't condition it to be plus bar or minus one. You just leave that part of the boundary free. What you get is a random curve that it also converges to SLE, to a variant of SLE called dipolar SLE, or SLE kappa minus 6 for again kappa equals 3. Then you can look at many variants of many configurations of boundary with boundary conditions that generate curves and prove that the resulting scaling limits are indeed conformal invariant and moreover can be described precisely by the Schramm-Levin evolution. A recent result of Stéphane Benoit, Hugo Duminil-Copin, and myself is about some interfaces that are somehow less generated by the boundary conditions than those. This boundary condition clearly forces the existence of an interface. This one also, and that one certainly also. Here you ask the question, okay, just look at the Ising model with purely free boundary conditions. What does the picture look like? And the answer is that, well, you have many curves that are interfaces. Actually, they make a collection of arcs, plus inside the boundary of the clusters inside are loops. Okay, so you get a picture like that. And question we addressed was, okay, what are the collection of all these curves that go from the boundary to the boundary, analogously to those? But what is the collection of all of them if you have free boundary conditions? And we could address this question using some sharp estimates about the way interfaces would behave near the boundary, and using this result saying how interfaces would behave when they are far from the boundary. So basically, the idea is that interfaces, when they are far from the boundaries, are something like that, because on their left they have minus spins, on their right they have plus spins, and the rest is free. And when they are close to the boundary, well, they don't stay too long on the boundary, so they bounce quickly enough so that we can identify uniquely the scaling limit of a certain exploration process analogous to the one Sheffield defined CLE with, and prove that the collection of all the arcs can actually be constructed from one or two random trees that describe the Ising configuration and that converge to a random tree made of SLEs. Okay, and so where is it leading us? Why, what can we do with that? Well, for instance, there is a natural question, maybe the most natural of all the questions. Here is, what is the scaling limit of all the collection of all the loops that arise with plus boundary conditions? So, in the talk tomorrow, of Antti, I think tomorrow, he will discuss similar question for the FK Ising model. He will discuss the loops that touch the boundary in the FK Ising model. The thing is that for the Ising model, the loops don't touch the boundary, because the value of kappa equals 3, is such that precisely the loops are simple and they don't touch the boundary. So how can you approach such a picture? Well, there are several possibilities, but one possibility is to say we can somehow couple this model with an FK Ising model whose loops touch the boundary, whose outermost loops touch the boundary, and conditionally on these loops of the FK Ising, the Ising, the original Ising model that's coupled with it, has 3 boundary conditions inside of each these FK loops, and hence can be explored by exactly this construction. So that's some ongoing work in progress, and I hope I'll be able to tell you more about it in a few months. Okay, so that's essentially all I wanted to say about interfaces. Now I'd like to discuss a bit random fields. So this is a picture that is somehow related with the proof, not so much with the statement. It's just a picture I think is nice, so put it there. So what are the fields of the Ising model? The fields of the Ising model are there are several possibilities. The most natural is the spin field. So you think your Ising model configuration is a collection of plus minus ones living on each vertex, and so you can ask the question: okay, do you have a random field taking values plus or minus 1? Is there a continuous random field to which this discrete random field converges, say in distribution? And the answer is yes. There's another field you can look at, the energy field. So remember, the energy of the Ising model is minus the sum over all pairs of adjacent vertices of the product of the spins at these vertices. So every pair of adjacent vertices, every edge, adds either plus 1 or minus 1 to the energy, and so you take an Ising model configuration, it has a certain energy, and you can ask how is it distributed across the domain, because it's localized on the edges. So are the edges close to the boundary more energetic in some sense than the ones inside, or the other way around? So that's the energy field. That's another field. Well, the strange thing about this one is that it doesn't converge to a random distribution, even though it can be studied in the limit. So now we have a certain number of results in that direction, explaining how these fields converge to some scaling limits that could be described by conformal field theory, for instance, or can be described by random distribution theory. So the energy field, that's already an almost old story. That's what we did with Stas Smirnov during my PhD thesis. And now recently there are fairly exciting results about renormalization of the energy field. It's somehow an easier field to deal with than the spin field. And actually now there's been much progress understanding these universality questions that Wendelin spoke about as far as the energy field is concerned. Okay, and so the spin field, as I said, is the most classical, the most natural, and actually the most observable field for the Ising model. This is really the field that people look at when they do experiments. That one can look at doing experiments. When you scatter neutrons on a thin layer of material, what you would typically see would depend on the Fourier transform of the correlations of the spin field. So this is really the most natural object, and for that reason there are many people who've looked at this in the last 6 years. The one who initiated that was certainly Onsager, and there are many people that did many things, in particular Julien Dubeda, who's here, has done really impressive work understanding the spin field and relating it to dimers, and then understanding the limits of dimers. And the spin field, so that's the next slide. Somehow I'm going to speak in more detail about that. But somehow using results described either here or there, there was a positive answer as to whether the spin field has a scaling limit that's a random distribution, random Schwarz distribution, by Kamiya, Garma, and Newman. Okay, so what is the result about fields? What is the result about spin field. So the simplest statement that captures the most, I would say, is this one. So if you take any domain of the plane, okay, and you take any collection of points and any reasonable boundary condition, say plus, for instance, okay, or 3 or minus, or plus minus, or plus 3, you can do essentially anything. So you take any domain, any boundary condition, and any number of spins, and you look at them on the lattice level. Okay. You look at the expectation, it's a number. So this number, as the mesh size goes to 0, and as was suggested by the picture I drew before, it goes to 0 as the mesh size goes to 0. But so it's just a hint that you should renormalize your field in the right way. And the way you should renormalize your field is just by the mesh size to the power 1/8. And as a result, if you take n points, you should renormalize by the mesh size to the power minus the number of points over 8. So if you renormalize by that, that's where you make the connection with conformal field theory. Because what you get in the limit, as the mesh size gets finer and finer, again at critical temperature, what you get is a function of the domain and of the point. And this function here, we were able to make it completely explicit by with Dimachelkak, who's here, and Kostya Dura has it here. I mean, Dimachelkak is here, but he's at ETH. Kostya Dura is not here, but he's in Helsinki. So we were able to make it completely explicit and to obtain that it was a constant to the power n, number of points, times the function that people in conformal field theory speak about. So this function displays conformal invariance in this way, that if you try to relate, you know, the function you computed in a domain, and the function you would compute in another domain, at the points that are the image of with the conformal map from the first domain to the second domain, that's how the correlation in the first domain and the second domain are related. And they are related in a way that's the most transparent and natural way that could be. Because if you think that just rescale your domain by factor 2, so make it twice as big, you cannot have the same as before, because if you make it twice as big, it's really the same as if you divided the mesh size by 2. And you should gain a factor here. And that's exactly what this factor is. So what you see here is that somehow the relationship is the simplest you could expect between fields into domain. And that's because you have this simple relation. That's why the spin field is called a primary field. In some sense, it behaves in a nicer way than other fields. Think if you took the derivative of the spin field. That wouldn't behave in as nice a way. Okay. Okay, so, well, you know, it's conformal invariant, and we have explicit formulas. So the one-point function with plus boundary conditions, that somehow was the subject of a few lectures last week, is obtained by taking the derivative of the conformal map that sends your domain to the disk, sends x to 0 to the power 1/8. Okay. The two-point function with plus boundary conditions, for instance, is obtained as a product of the one-point functions times an interaction term, which depends on the hyperbolic distance between the points. So this correlation blows up like 1/the distance to the power 1/4 as x and y get closer, and it vanishes. No, it goes to 1 as x and y get further apart, so the correlation vanishes. So this was predicted by John Cardy. This is an obvious prediction from that somehow, but this is not completely obvious. It depends on the boundary condition, etc., and it was predicted by John Cardy. The general case was predicted by Burkhardt and Kim in a paper of the early 90s, and they were able to obtain some very impressive formula for the half plane with plus boundary conditions that are reproduced here, and we were able to prove that these formulas indeed were right, which I think I would like to emphasize seemed much needed, in the sense that those formulas were only obtained for small numbers of n, like n equals 3, 4, and extrapolated for other values. So I think there really wasn't need, even from a physical perspective, for extra confirmation that these formulas are right. Okay, so then you can generalize with other boundary conditions. Okay, so now let me just try to give a quick idea on how the proof works. It's a fairly complicated proof, but I can give one idea which somehow lies at the very heart of the paper. It's an idea that is about how you can compare the values of two adjacent spins. Somehow this question is not so easy to attack directly. I mean, it's easier to see how this varies when you just move a little bit one of the points. So the question is, how do you compute this limit? So if you take the ratio of two expectations of spins at adjacent locations, this ratio should converge to 1. There is no reason why this spin should be much more often plus than that one. So it converges to 1, and if you subtract the 1, then it's natural to expect that since the limit is a function of the points, that the difference between two adjacent points is of order delta. So if you divide by delta, you should obtain some kind of derivative. I mean, namely, you should obtain a logarithmic derivative, because if you put things on the same denominator, you should get the derivative divided by the function. That just is the logarithmic derivative. You should get the logarithmic derivative of precisely this function, which is what you conjecture is the limit. So how do you prove such a convergence result? That's really a key place where the connection is made between discrete world and continuous world. So the idea is to construct a lattice spinner, which I don't have the time to define here. It was explained in some more detail in the lecture. So basically, without really looking at the definition, we can say that it's a function of the points we look at plus an extra point. This function is defined in a combinatorial manner using some Riemann square root surface considerations, but okay, it's a sum of the pictures. The pictures depend on the points. Anyway, it's a function of an extra point in the original points, such that it satisfies local relations. It is namely discrete holomorphic, and when you evaluate it next to the point where you look at the spin, you get the quantity you want. So you have a function that satisfies the lattice analog of Cauchy-Riemann equation. So something that's pre-holomorphic, if you wish. It's to be expected to go into holomorphicity in the limit, and that gives you the right value at the right place and has some boundary conditions. So that's where all the exact solvability of the model was put in the construction here. Okay, so because the model satisfied some miraculous relations, one was able to rephrase these miraculous relations into much simpler, into relations that a priori are much simpler, namely this discrete holomorphicity. What's good about these relations is that they scale well. You have a relation for essentially every vertex, and what you do with these relations, well, it's not very complicated. They scale very, very well. They are linear relations. In the limit, you should obtain continuous holomorphicity, and that's going to be your continuous relation that describes the limit of the integrability of the model. So it's fairly, that's really the message here, is that you need to connect a model when it's discrete, when it has exact solvability with some form of exact solvability that will scale well in the continuum. So, and here, as in most of the results for conformal invariance, the exact solvability arises as discrete holomorphicity. So, in the end of the day, what do you have? You have put all your hopes, all the relations of your model into this spinner that gave you the value, and the spinner converges to a continuous spinner, I mean function that takes values like a square root. That's what I mean by spinner, nothing else. So you have this function, it converges to a continuous holomorphic function. You can identify exactly what this continuous holomorphic function is, and you can tailor expand that holomorphic function around the point where you're interested in. And what you get is that the second coefficient in the Taylor expansion is exactly related to the limit of this term. Somehow the first term is a 1, the bold 1, and this 1 represents this 1 that you have to subtract here. And once you have subtracted that 1, Once you have somehow killed the singularity, and the next term is the interesting one. Okay, so that's how it works for the one-point function. How it allows you to compute ratios of one-point functions at various places, and you can do a similar approach, albeit a bit more complicated, to do endpoints. And in the end of the day, you're able to compare endpoint functions on the same domain at various locations, and then you need to merge all this data you have extracted to obtain really a result that allows you not to compare to that allows you to say something definite about one domain, not the ratio of things, and that uses somehow probability on the discrete side. I mean, inequalities like GHS inequality, FKG inequalities, and on the continuum side, some estimates about the behavior of holomorphic functions. Okay, so that's more or less how it works. Of course, it's not super easy to reconstruct the proof from just this explanation, but the goal is to give a flavor of what happens. Okay, so now I'd like to discuss something completely different. So we proved somehow here, conjectures coming from conformal field theory, if you say that conformal field theory is just a collection of formulas. Okay, but conformal field theory is not just a collection of formulas. There was a way to obtain these formulas. And I think it's an interesting question to understand how these formulas were obtained, and especially so because they were obtained in a way that is different from the way we obtain the formulas. Okay, so there is some structure that is used in CFT that we have not revealed in the model, and it's interesting, especially because these structures, even though we don't have clear hopes to make them rigorous for other models at this point, these structures, they should be fairly universal, at least as universal as SLE is, in some sense. So, well, Julien Dubeda is going to explain how the Virasoro algebra is connected, how the CFT is connected with SLE. But I want to speak today about how the model we look at should be connected with conformal field theory. So, in order to explain that, to give a hint of what happens there, I need to explain a bit what conformal field theory is, what it does for you, and what it is about. If you open a CFT book, it might not be obvious that it is about the same object. So, because there is a strong emphasis on different things. So, indeed, CFT allows one to derive correlation functions for conjectural scaling limits of models. That's certainly true, and that's really what we proved here. In most of the cases where there were conjectures for the Ising model, we proved those conjectures. Okay, but now the question is, okay, what is the central tool? Actually, there should be an S here. There's maybe two central tools. For one thing, it is purely algebraic theory, the study of representations of the Virasoro algebra. What is a Virasoro algebra? What is a representation of the Virasoro algebra? A representation of the Virasoro algebra is just a collection of operators, ln. ln is an operator, n is an index that is a positive or negative integer, so ln for n is z. And it's a Lie algebra, so a representation of the Virasoro algebra is a collection of operators, L1, L0, L-1, etc., infinite number of them, such that their commutation relations is this one, where there is a free parameter somehow. Okay, there's a parameter, and it's a number, and this number is called the central charge. So the idea is that big part of CFT is somehow rigorous study of this algebra. It's not so easy to study this algebra, but it can be done. Okay, and then there is the geometric interpretation, what this algebra means for a model. And okay, it's just to make a big jump, but how things work. Hiding all the details, ignoring all the details, one can just say that, okay, this study yields us PDEs. And the PDEs are, what are the PDEs good for? Well, the PDEs tell you what differential equations such correlations should satisfy as function of the point. Well, SLE tells you some PDEs, but CFT tells you other PDEs. Some of them are the same. difference. Okay, so or at least a priori martingale equations for SLE give you some type of PDEs, and here you should get some other types. Some PDEs, these PDEs plus other ones. Okay, so in CFT, when you say a model is conformally invariant, that's an assumption. That's not a rigorous statement usually, and this assumption is translated not in the way I explained with the domain getting mapped to another domain, but rather translated directly into an algebraic statement that the Virasoro algebra acts on the model, and well, with a parameter depending on the universality class of the model. Ising model should be C equals 1/2, Gaussian free field should be C equals 1, three-parts model should be C equals 4/5, etc. Okay, so a natural question is, yeah, okay, so it seems that there is a big jump. Somehow there is the Virasoro algebra that arises in the model. So how does it arise in the model? Okay, can we understand that for a nice lattice model? So that's a question that I think is very interesting, and I've been working on that for a few years now. So let me explain what's written in the physics book in hopefully a language that makes it a bit more concise and understandable in the probability talk. So CFT is about fields, sorry about the D. So it's about fields that we call maybe O, which are to be understood as scaling limits of properly renormalized lattice fields. So for instance, I would write sigma for the scaling limit of the spin field, or write maybe epsilon for the scaling limit of the energy field. So the fields don't need to exist, in a measured theoretic sense. They just need to exist as scaling limits of correlations of lattice correlations, for instance. So it's about fields, objects that are not extremely well defined, but what you know about the field is that you at least can take its correlations. So a field is just somehow, in a very crude manner, it's just something you can take correlations of, something you can form an expression of with these symbols, a bracket here, a field here, a point here, a product here, another field here, etc. And you close the bracket and you put a domain and you put some boundary condition. And when you close this, there's a number. So it's a function, which is a function of the points, assumed to be an analytic function of the points, and a function of the domain of the boundary conditions. So a field, really in a crude manner, it's just something you can take correlations of. But the way you should think about it is really a limit of some lattice fields, especially if you're studying C equals 1/2. You should really think of a field as a limit of Ising model field. Okay, so you have these fields, they form a vector space, and they represent the scaling limits. Their correlations represent the scaling limit of the correlations on the lattice space. Okay, so now where does this Virasoro algebra come into play? So the idea is that the Virasoro algebra acts on the space of fields. So what does it mean? Again, as I said, the space of fields is a linear space. You can take two fields, you can multiply one field by two. Of course, it will add, this thing is multilinear in each of the fields. So if you multiply the field O1 by 2, then you multiply the correlation by 2, for instance. Well, you do all the things you would expect from the limits of lattice fields, eh? So this Virasoro algebra acts on the space of fields. So for every field O, ln O is a new field. Okay, you have a field, you get a new field. How is the field defined? Well, fields are only defined by the correlation, so you just need to define what is the field at one point. So the field at a point Z is going to be defined as a contour integral on a small contour surrounding the point Z of your field times another field, T of zeta, integrated times zeta minus Z to the power n plus 1. So it's like a Fourier mode where you have somehow reweighed your original field by a new field. This new field is a special field called the stress energy tensor, or more precisely the analytic part of it. So when I write such a formula, again, I mean it is true within correlations, okay? When I take correlation of this guy, I take the contour integral of the correlation of that guy, okay? Again, fields, in our minds, they are limits of lattice fields. But if we really ask for definitions, they are just things we can take correlations of. So I can totally define a new field by a formula like that, provided this guy is an analytic function so that the contour integral doesn't depend on the choice of the contour, provided the contour is small enough. Okay? So there's this field, and so the definition of the The field again is contour independent when taken within little brackets. Okay, so that's really how Virasoro acts. I mean, the main action of Virasoro in the CFC is that you send a field to another field by an operator ln with this simple formula, and that if you look at ln of lm of a field minus lm minus ln times ln of a field, you get that is the same as n minus m times ln plus m of the field plus c over 12 n cubed minus n times the field. Okay, really, you send a field to another field, and the way you do it satisfies the Virasoro relation. Okay, so now there is a geometric interpretation, but I won't have time to discuss it. There is still a question. The immediate question is, where does this come from? And so here's a hope. Here's a question: could we make sense of this idea on the lattice level for Ising model, for Gaussian free fields, etc.? So what should be, why should it work? A priori, there is no reason why it should work, and people didn't think it worked until we found something. But the idea is that you should have some exact solvability on the lattice model, which you translate into discrete complex analysis. So far, what we have done is use discrete complex analysis to go to conformal invariance. And somehow, if we understand conformal invariance in the same way as physicists do, we should get this Virasoro algebra. But what if there is a shortcut? Direct connection between discrete complex analysis and Virasoro. Priori, there is no reason, but maybe still there are reasons. So what are reasons to believe that it should work? So we have discrete holomorphic objects for nice models, like Ising models. We have this fermion, which I denote by psi. And, well, I don't want to define too precisely what the fermion is, but the fermion is at the very heart of this guy. There is a fermion living at z for any point z. It's not exactly a probabilistic field, but it's essentially very close to one. So you have an object for the Ising model. I don't want to define what it is. We have one for the Gaussian free field, the discrete Gaussian free field, and this one is easier to explain. Just take the difference of the Gaussian free field at two endpoints of an edge. That's a field that lives on the edges. That's a current, lattice current. So this guy is also discrete holomorphic for the reason that the Gaussian free field is discrete harmonic, for the reason that is defined from the Laplace, discrete Laplace operator. So well, again, what I mean by discrete harmonic for the free field, I mean correlations of the free field are harmonic as functions of the locations. I don't mean the field realizations are harmonic, rather the expectations you take when you take at non-coincident points, they are harmonic functions. So okay, you have these nice objects. Of course, the GFF you never do discrete complex analysis because they are central limit theorems, and it's much it's Gaussian already from the beginning. So it's much easier to do without complex analysis, but in principle you could. Okay. So anyway, so we have discrete holomorphicity here, and the good news, but that's not something that was really written anywhere in say mathematical physics. But if you have a discrete holomorphic function, so you can take discrete modes of it. You can really discretize properly, this contour integral somehow. The function times d to the power n dz. Well, that might seem trivial if it's a good discretization. It's fairly trivial combinatorially speaking. It might be a bit surprising if you have heard this thing that the product of discrete holomorphic functions is not discrete holomorphic anymore. Well, anyway, you can still define this. Okay. You can define this, but say you cannot define integral of f times g times z to the n dz. You cannot do that, okay? And that turns out to be a problem. Because if you read conformal field theory books, they'll tell you the stress tensor should be this for Ising and should be that for GFF. Well, the question is why this? That's also some work in progress to explain why the stress tensor of these things are what they are. I mean, this has been dealt with by Kang and Makarov, I believe, in GFF paper for the continuum from a probabilistic perspective. And this, there's parallel work in progress of various teams that grew up in Geneva. About that, there is Chalkak, Glassman, Smirnov. They're working on something with Stéphane Benoit, and I'm also working on, on a similar question. And with Alexander Glassman, I'm also working on yet another similar question. Well, anyway, so there is, maybe the main question here is, the first question is why, okay? But okay, believe that, take that as definition of t. So for GFF, say it's just the square of this derivative, discrete derivative, this difference. So now it's a problem. You cannot define the modes of this guy on discrete level because this is not discrete holomorphic anymore, okay? The square, discrete holomorphic guy is not, because the square is not discrete holomorphic. Okay, so there's a problem here. So we have a solution. So solution, it's the so-called discrete Sugawara construction. So the idea is, okay, we'd like to define for Gaussian free fields the modes of this square on lattice level. But we can only define the modes of the poor guy, not the square on lattice level. How do you do? What do you do? Well, it's a fairly simple when you think about it. You just think, okay, actually we cannot define the modes of the square, but the modes of the squares is the convolution of the modes. If you think in Fourier world, the Fourier transform, the square of a function is the convolution of the Fourier transform of the function with itself. And so that's really the idea, simply, that you can define modes of the simpler objects, so the fermions and the currents, that discrete holomorphic, and that then you can define the lns that you wanted to define as just convolutions of the modes of the simpler objects. So I think there is a small message here that's important, which is that whenever you can linearize, do linearize. Here we have a square. Here we have a product that's not linear, and we can only deal with a linear thing. But somehow, if you really want to, here you can linearize by saying that the modes of the nonlinear thing is the convolution of the modes. Of course, in the continuum, it sounds like a small, as a kind of way to make your life more complicated, to take modes as convolution of modes instead of taking the square. But in the discrete, that seems to be the only reasonable way, and that's why it was not so obvious to start with, but that's a small idea. Anyway, so you define the modes. Okay, you define the modes. You can define these operators. You're lucky enough so that there's only a finite number of such operators that is not zero when you evaluate in a correlation, so it's good. And now you prove that you have commutation relations between these simpler modes. You get them. It's exactly the same as in the continuum. That's good. And the nice thing is that if you want to compute commutation relation of those figure guys, you can just play with this little algebra for a while and obtain the commutation relations that you should, namely that the Virasoro algebra for Ising is C equals 1/2, and Virasoro algebra for GFF is C equals 1. So I think there's also something cute happening here. So you find a full algebra already on lattice level somehow. Okay? Not just a twisted version. Really, the full algebra is already there on lattice level. And I think that's cute because in SLE you're not going to see the kappa on lattice level. There's no way you're going to see the kappa on lattice level. However, for the algebra, you see the right thing already on the lattice, the right structure already on the lattice level. Okay, so that was a strategy how we can hope that things work. So here is not exactly a precise statement, more precise statement. So that this Sugawara idea, which appeared first in string theory, can be discretized and defined as follows. So let's just take one step back and ask the question, okay, what do we want to do with the field? So take a domain. If you take a domain, you take a point in the domain, and you ask, okay, now I want to just take a look at one point function, say, of a field at that point in the domain. So if I think, now I fix the point in the domain, and I look at this as a function of the field, I have a map from the space of all the fields that sends a field to its correlation, which is a number. So it's a linear map, as it should. Well, okay, so that was for one point. If I wanted to take two or 3 points, I could just do a map from the tensor product to here. That's about the same. I just took one point because it's simpler. So that's a linear form. So you have a space of linear forms you have a collection of linear forms because for every domain you have a linear form. Every domain, any position of the point, You have a linear form. And now you can define, so that's still what one could do in a CFT book in the continuum. One could define a dual action of the Riaso algebra of such forms. So the ln dagger of a linear form would still be a linear form, and it would send a field to ln of it. So that's a new field by the Riaso action at the point z in omega. Okay, so you transform a linear form into a linear form. That's just a dual formulation of the original formulation. Dual in the sense linear algebra dual. Okay, so now the good thing is that this is fairly easy to discretize. So on lattice level, what are fields? Fields are what I call lattice local fields. So just a function of, say, for Ising, a spin at a point, and a spin at the neighboring points, and maybe a finite number of neighbors, just a finite number of neighbors. Okay, so it's a function of just a local graph neighborhood of a point. So that's a field for us. That's really how we think about a field. Like the product of two adjacent spins, that's the energy field. The difference of two spins, two adjacent spins, that's the derivative of the spin field. That's really the way we think of the field. So, so the fields are these guys for us on lattice level. Let's agree that this is a reasonable definition. And now the idea is that, okay, if you have a domain in the continuum, you're going to replace it by a discretization of it. So a sequence of graphs that approximates the domain better and better. So for a domain discretization, what we have is you have a family of linear forms that sends one field to its correlation. That's an expectation somehow. That's an expectation in the domain with the boundary conditions you want. And so that's true for any delta. You don't go to the limit, you just say you have a sequence. Actually, this sequence, this guy is only defined for small delta. Depending on how big the support of your lattice field is, you'll need to go a bit further in the sequence. But the only thing that matters is somehow the tail of the sequence, okay? So you have a family of linear forms, and the claim is that we can really act on the space of such forms on lattice level by really doing ln's that are these guys, and these guys that are discrete contour integrals of those guys, and we can really mimic the construction. So, a comment about these linear forms. That's really reminiscent of Gibbs measures. How you define Gibbs measures? There's maybe the most natural way is you take a sequence of domains that gets bigger and bigger and goes to the plane. I think, what if you don't take the limit of the sequence, but just the whole sequence itself? Because if you take a collection of you take a domain and you discretize it further and further, the graph gets bigger and bigger. But if you take the whole sequence and not just the limit, you'll be able to see in that sequence any correlation of any CFT field you want, because it will be just a properly renormalized limit of things. But the claim is that we have an action on the whole sequence, so already at the discrete level before passing to the limit, and you can act on this limit, and somehow the claim is that these families, they contain as much information, all the information that these families contain, at least contextually, so if you can act on this, you can really say, well, we acted on lattice level. Well, there are several kind of dual ways you can define this action, but I think that's somehow the simplest. And so we can act on the space of such fields. Again, CFT correlations are obtained as some renormalized limits of these correlations. And that's the main message, that things can be discretized by replacing these guys by really discrete analogs of them. For the positive powers, for the positive monomials, you're just going to integrate the function identity n times, basically. For the negative monomials, you're just going to differentiate the Green's function n times. This contour integral will just be a finite sum, contour independent, and things work out quite nicely. That's the claim. Okay, so I'm almost done. So there are still some things that are going on. In particular, there's a question I mentioned about lattice stress tensor that's quite interesting. And in the end of the day, why you want to look at these lattice local fields, etc. Well, there's really something I'd like to understand. It's not there yet, but I mean there has been some small progress. Is to understand the Ising model with a magnetic field. There is a somehow solution in the CFT literature by Samolotchikov, but how the Ising model with magnetic field, which is not a solvable model, should become solvable in scaling limit. And my understanding of how possibly one could make this solution rigorous is by precisely making sense of this Virasoro action on lattice level. And this is a picture of E8, of the E8 root lattice done by hand. I mean, like with threads and needles, basically. And somehow this E8 should describe somehow the scaling limit of the magnetic Ising model. Ising model with magnetic field. And finally, a conjecture, which is like, okay, you have this action on this field, and the idea is that now the ways of renormalizing these things these correlations will depend on the field you feed them with, but there will be essentially three families of renormalizing, and we should, that's what a conformal field theory says, that there should be three families, and I think we are not so far from proving that, but I'll still state it as a conjecture because there are many things we have not sorted out. So anyway, thank you very much. Questions?
Questions?
Yeah.
In physics, there is this picture of the Ising model with the conformally invariant phi-4 field.
By
this conformally invariant phi-4 field. You know
okay, so that's a good question. Yes, that's a conjecture, but not everyone agrees on that. I think it is correct, but the arguments why the critical phi-4 field theory should be Ising model fields is by counting the number of primary fields that should be in the phi-4 theory, in the phi-4 critical theory, and seeing that it has a ±1 symmetry. So I would say the argument, is not extremely strong. I believe it's true, but we don't have as many good reasons to believe that as we have for other things. So yes, it is believed, but it's not very well argued, even.
And conversely.
Sure. So the phi-4 field, the phi field itself should be the spin field. So a statement would be that the scaling limit of a spin field is the same as the critical phi field in the phi-4 field. Then the energy should be kind of weak square of the phi field. This is believed. Okay. There's a counting of the number of relevant fields in the phi-4 theory, and it matches the counting of the number of relevant fields in the Ising model, but that's very, very, very weak as a way to connect the model. So I believe if we could prove conformal invariance of, existence and conformal invariance of the phi-4 theory, that would really help a lot. So maybe if we had that, it would not be so hard. Otherwise, I don't think it's going to be done anytime soon. Yeah?
So about your proof of convergence of correlation functions on the spin field, where does the power 1/8 come from?
Okay, well, there's different reasons why the 1/8 comes from. In no proof, it might seem a little strange, but there's just a constant here that appears in the explicit calculation. Okay. Okay. The coward answer is that Dima will speak about it. Okay. That's really a cowardly answer. Okay. So if you basically, if you look at the log, d log of sigma x omega. So the log of this is d log of phi prime to the power 1/8. Okay, and phi prime is the derivative of the conformal map, whatever you say. And so this is 1/8 d log of phi. Okay, so you should see a 1/8 constant when you compute this logarithmic derivative. So now, where does it appear? Basically what you do is you solve exactly this continuous boundary value problem, say in the half plane, you solve it, or in the disk you solve it, and you see what is the constant in front of the what is the value of this by Taylor expanding it, and you see, oh, there is a 1/8 in the second Taylor coefficient. Okay, well, so the answer is that, you know, it's not the better answer. Like, why is necessarily 3 kappa equals 3 the getting limit of of the Ising model? You write a Martingale extension, and you see there's a 3 number.
In what you wrote on the proof, like you do a ratio of correlation functions.
Yeah.
So the randomization factor like disappears.
Yeah, that's the trick. That's what allows you to speak about the 1/8 without knowing about the 1/8 at priori. Right. That's really the whole point. Is that the last thing you want to do is do discrete complex analysis with a delta over 1/8 renormalization of your holomorphic function. It's the last thing you want to do. Well, you would have to have a manifold monodromy to be non-zeros. Would be a nightmare. So that's a good question. Yeah.
Just by curiosity, at the beginning of your talk, you mentioned a few names, like among them Spencer, about renormalization techniques.
Right.
What's it about?
So it's a not so well-known paper that proves that in the full plane, energy correlations exponent is 2. Even for an Ising model that is not integrable, an Ising model that has non-nearest neighbor interaction, so it's not exactly solvable. So it's a perturbative approach that tries to compare Ising model integrable one with a non-integrable one, and that shows that some critical exponents, like the energy exponents, are preserved. If you move on the critical line, but you change the coupling strength, so basically the nearest neighbor become less correlated, but you have correlations with the next to nearest neighbor, and remarkably you get still that the exponent is 1 for the energy field. That's what they prove. So this has been refined by Maestro Pietro and Giuliani, and there's been, now there's a very nice paper, I think, of a few authors from that school from Rome that really proves a scaling limit in the full plane of all energy correlations, and actually more than that, with beautiful, renormalization technique in momentum space, not in real space like Vandeling discussed, but in Fourier space. And that's really, renormalization in the way that was written in physics book that was made rigorous for the energy field. For the spin field, it doesn't work yet, but yeah. Okay, thank you very much.